Good afternoon to everyone. I am Mujibur Rahman. I will be taking the session 5 of this problem solving sessions on the course Advanced Soil Mechanics. The course instructor for this course is Professor Srideep Shekhar, who is the professor at Department of Civil Engineering, IIT Guwahati, and I am a TA for this course. I am from the Department of Civil Engineering, IIT Madras. So in the last week, we have seen that the shear response of cohesionless soils and cohesive soils, and we came across the different formulations for determining the failure criteria also. And at the end of this session, or the week 4 content, we were introduced to the terms the drained and undrained conditions. I will briefly explain that in the drained condition, what is happening that the rate of loading is such that whatever the pore water pressure is generated, it's getting dissipated, and it's the material property also that allows this pore water pressure to get dissipated. It depends upon the permeability characteristics of the soil also. But we have seen another condition why the rate of loading is so fast and the soil is not able to dissipate this pore water pressure immediately, which results in the generation of the pore water pressure in the soil. So these conditions we called it undrained conditions. So how the things are different in these two drainage conditions is that in the drained condition, due to the dissipation of pore water pressure, there is the volumetric change that will happen in the soil. But in the undrained case, since the conditions are undrained, we are not allowing any pore water pressure to dissipate, there will be no volume change. Now in this week 5, we will start with the typical differences in the responses if we talk about the drained and undrained condition. So it's the play or the gameplay of the pore water pressure which is actually governing the two different behavior in the soils. So we'll go through them one by one. So we have seen that when the total stress is applied on a saturated soil mass, there is an increase in pore water pressure. Yeah, this is true. Like whenever we are applying the total stresses on the soil, there will be the increase in pore water pressure. Now, whether the conditions are becoming drained or undrained, there will be the dissipation of this pore water pressure. In case the conditions are undrained, there will be the continuous, and this, I think this statement is true for the undrained case, because there is an increase in the pore water pressure. And rate of loading, rate of the applying total stress, and the rate at which pore water pressure dissipates are critical factors that govern the mechanical behavior of the cohesive soils. Now, how this total stress is being applied on the soil and the rate at which this pore water pressure gets dissipated, they actually govern the mechanical behavior of cohesive soils. Now, two things are now there. One is the drained case and another is the undrained case. You will see that for a same soil, if the conditions are becoming drained, how the behavior of the soil is different from the condition when the conditions being prevalent in the soil is undrained. Let's take a construction sequence example where initially there was no construction or there was no building on a soil deposit, but as soon as we have constructed the building, we are assuming two conditions. One is the drained response and the undrained response. As I told you, drained response means we are allowing the pore water pressure to dissipate, and undrained response means there is no dissipation of pore water pressure. Now, initially when there was no construction or building, the stresses were zero. External stresses or the change in the stresses, total stresses were zero. As soon as we start constructing a building on a soil deposit, the change in the total stresses begin to increase till it reaches the completion of the construction. Once the construction ends, then there is no change in the total stresses. Correct? So this line, increasing line, shows the construction period of the building. Now, since the conditions are drained, there will be no generation of pore water pressure. So the pore water pressure variation is zero. So according to the Tarzagi's equation, effective stress is equal to total stress minus pore water pressure. Since the pore water pressure is dissipated, so whatever be the change in the effective stresses, it will be due to the change in the total stresses. Correct? So that's why you can see the same variation of the change in effective stresses as we have observed in the change in the total stresses. It's because the pore water pressure is not getting developed in the drain response. So the variation is it increases up to the time till the construction of the building is complete. Once the building construction is complete, the total stress or the effective stress will also become constant. Now we know that for in the soil, we know this is a very famous concept or very familiar. You will be familiar with this, that effective stress actually bring the change in the compressibility characteristics of the soil. So with the increase in the total effective, with the increase in the effective stresses, there will be the volume change in the soil sample. Since the effective stress are increasing, it's obvious that it will bring the compression or it will compress the soil. Correct. So this kind of behavior we are observing in case of drain response when there is a change in the total stresses. Now we have the same scenario, but now the only difference is that we have an undrained response. We have the undrained response. Now the first figure will remain same, that like the building, as soon as we start constructing the building, there will be change in the total stress of the soil will be experiencing till it reaches the completion time. Once the construction of building stops, the total stresses will not change. Now in this case, in the undrained case, we are not allowing the pore water pressure to dissipate. What will happen, that whatever be the delta sigma, whatever be the stresses coming from the total stress, or whatever the stresses are coming from the construction, they are actually going to change the pore water pressure, delta U. Correct? That's why. And whatever be the change in delta sigma, the same change will be observed in the delta U in case it is a saturated deposit. So whatever be the change in delta sigma, the same change will be experienced, same change will be there in the pore water pressure till the completion of the building. Once the building construction is over, once the total stress remain constant, now here it depends upon the permeability characteristics of the soil. How the permeability of the soil is, whether it will dissipate this pore water pressure quickly or it will take some time. In case, and accordingly the effective stress will be developed in the soil. You can see that in this phase, again if we use the Terzaghi's equation, sigma dash is equal to sigma minus u. The sigma and u, the change in the sigma is same the change in u, so total effective stress developed will be 0. So that's why you can see that for this initial portion there is no effective stresses, and also there is no volume change also, because the volume change is brought by the, or the volume change is due to the effective stresses. So in this phase, in the loading phase, there is no effective stress in the soil sample. It's not getting developed, so there will be no volume change. Once this pore water pressure start dissipating, there is the increase in the effective stresses, and once the effective stress start rising up, there will be the corresponding volume change. Now let's assume at any time t, whole pore water pressure gets dissipated. So delta U at some time becomes 0. Delta U becomes 0 at some time, that's 1 year, 2 years. So at that time, what will be the total stresses? Delta sigma, that will be equivalent to delta sigma dash. Correct? So at once whole pore water pressure is dissipated, so at that time, whatever be the total stress, whatever be the total stress present in the soil, that will reflect in terms of the effective stresses. Thus, we can say that even if the material was same, the difference in the drainage conditions bring a significant change in the response of the soil. That's why this statement has been written that the rate of applying total stress and the rate at which pore water pressure dissipates are the critical factors that govern the mechanical behavior of the cohesive soils. So you have seen that how the drained and undrained response varies, even if we have kept the drainage, even if we have kept the loading conditions same, or even if the soil is same. Now, from this slide, or from this understanding, you can observe or you can understand the we can say the knowledge of pore water pressure, determining the pore water pressure becomes critical in certain scenarios where the undrained and drained response are actually influencing the mechanical behavior of the soils. So there is a need to predict them, to predict the pore water pressure at different stages of the loading, so as to understand the mechanical behavior and design safely. So that's why we have written that knowledge of pore water pressure becomes critical during undrained loading, For example, the feed conditions where undrained conditions are prevalent immediately after the construction. And the concept of pore water pressure parameters were introduced for predicting the excess pore water pressure under different loading conditions. That's why the coefficients, the pore water pressure parameters were brought into consideration in order to determine the excess pore water pressure that gets developed under different scenarios, different loading cases. The whole story is of this, whatever the lecture I am going to do or whatever the discussions we will do in this session, it will revolve around the how we can develop the equations for predicting the excess pore water pressure that's getting generated under different loading conditions. Correct. The first attempt for determining the pore water pressure at different loading conditions was done by the Skempton. He gave a well-known equation, and he has given some parameters also, A and B. That's why this equation is famous. We call it Skempton's pore water pressure equation, and the parameters A and B are called Skempton's pore water pressure parameter. Now, as I told, in the drain case, whatever the delta sigma is, whatever be the total stresses are coming, they are actually changing the pore water pressure, and this pore water pressure is getting now the delta sigma, in case of drainage condition, whatever the delta sigma we are applying, there is the there is the dissipation of pore water pressure. So pore water pressure is not getting developed, and this dissipation caused the volume change. See, as you can see here also, since the pore water pressure was here, the pore water pressure is dissipating, and correspondingly there will be a volume change. Here the pore water pressure is not dissipating, there is no volume change. Correct. So this change, this dissipation of pore water pressure is actually causing the volume change. So this has to be taken into mind. So it means that in the drain condition, this dissipation of pore water pressure brings about the volume change. But what about the undrained conditions? During undrained conditions, there is an increase in the principal stresses. It results in the increase in pore water pressure. We want to see how much this pore water pressure is increasing due to the increase in the principal stresses. Fine. So what approach they have developed is, they have considered a undrained condition with no drainage, and they have assumed that whatever be the change in the volume, it occurs due to the compressibility of water as a result of change in pore water pressure. They have started building the equation based on the assumption that whatever be the volume change during the undrained conditions, it is due to the compressibility of water. We know that there is no volume change, but if in case there will be a volume change, that this delta U can do, it will be equivalent to the volume change that has happened in the drained conditions. Correct. So this is for building the equations. They started with some assumption that whatever the volume change occurs with the compressibility of water, and this volume change is brought about by the change in the pore water pressure. So mathematically it can be written as this volume change minus delta V, because there is a compression, is equivalent to volume of water, compressibility of water, and the pore water pressure, and the change in the pore water pressure. It is similar to settlement is equivalent to mv delta sigma h, and this settlement, I can write it like this: settlement is equivalent to mv delta sigma into h, and this settlement is brought by this delta sigma. Similar to that equation, this equation has been developed. Now this is the volume of water. In case of saturated soil, since it is a saturated soil, if we use the porosity, it's volume of void by total volume of the soil, total volume of the sample, so we will get the volume of voids. In case of a saturated, if the soil is filled with water, so all the voids are filled with water, so it can be represented by VW. So this VW will be equivalent to N times V. So that's why we are using that equation here. Correct. And finally we got this equation: volumetric strain is equivalent to N times CW delta U. Now in case drainage is allowed, so this volumetric strain would have been equivalent to this thing. Correct. So this change in the volumetric strain is actually it has been brought by the delta U. Some readjustments are there, and you will get this equation: delta U is equivalent to 1 minus 2 mu divided by N times E CW into delta sigma 1 plus delta sigma 2 plus delta sigma 3. This equation is actually the basic equation, correct, for predicting the pore water pressure during different loading conditions in the soil. And here we are not a condition specific. It is for triaxial, it is for plane strain, or it is for axisymmetric. It is a general equation. Now, how we can use this equation for predicting the pore water pressure during the triaxial conditions? So we will be using some assumptions. We know that for triaxial conditions, the delta sigma 2 is equal to delta sigma 3. We know that the radial stresses are same, and after doing the readjustments in the equation, this equation, we will get delta u is equal to 1 divided by 1 plus n times Cw by Cs into delta sigma 3 plus 1 divided by 3 delta sigma 1 minus delta sigma 3. And this is the equation that corresponding to the triaxial condition only, correct? And this is valid for the saturated soil, and it's elastic, and the conditions are triaxial. And Cs here represents the compressibility of soil skeleton, which is given by 3 into 1 minus 2 mu divided by E. Again, I am repeating that this equation A, it's valid for saturated soils behaving as an elastic material and have a triaxial condition. And whatever you can see that there are two things, delta U, three things are there from the loading perspective. One is delta sigma 3 and one is the derivative stress. It means that this delta U is affected by the both loading conditions, whether it is in the confining stage or it's in the derivative stage. So in the both stages of the loading, this delta U is getting generated. Now, to make it more easier or for remembering, this can be further simplified into delta U is equal to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3, where this A is equal to 1 by 3 for perfectly elastic material. But we know that every material cannot be a perfectly elastic material, so we can keep it as a variable A. In case we are using a perfectly elastic material, we can replace it A by 1 by 3. And in another form, we can write in terms of B times delta sigma 3 plus A dash times delta sigma 1 minus delta sigma 3, where this A dash will be equivalent to A into B. Now, we have two things in it. One is the parameter B, and another is the parameter A, correct? A and B parameter. Now, this B parameter, if we look it carefully, this B is written as 1 divided by 1 plus porosity times Cw by Cs. In case the pore fluid is water, we can use the Cw term. In case there is any other pore fluid, we can replace the Cw by Cf. This is the equation that has been developed for B. Now, in case of fully saturated soils means there will be water in the voids. Therefore, this term, compressibility of water divided by compressibility of solid solids. The compressibility of solid solids will be very large as compared to the compressibility of water. So this term will be close to 0. Its value will be close to 0. So in that case, that B value will be equivalent to 1. B value will be equivalent to 1. Fine. Now, for dry state means there will be air. There will be air in the voids. When we have air in the voids, so the Cf will be very greater than Cs, correct? And the denominator will be 1 plus n times Cf by Cs will be very large than the numerator 1. So this term will become 0, correct? So it means that for this saturated soils, this B value, maximum value is 1, and for dry state, where there is no pore fluid, where the pure fluid is water, this B is 0. So the saturation, as the saturation increases, the B value increases, and the typical range of B is 0 to 1. B can be greater than 0, less than 1. And as the confining stress increases, or as the delta sigma 3 increases, change in the radial stress increase, B value also increases. That's why this parameter B is used in the triaxial conditions for ensuring the saturation of the triaxial samples, correct? Now, we have another parameter A. This parameter is equivalent to 1 by 3 for perfectly elastic case and triaxial loading, fine? And A changes with loading. And also or with the derivative stress. And since it changed with the derivative stress, there will be the initial A naught, or A initial and A final. A initial corresponds to the initial loading, and A final corresponds to the failure, correct? When the soil sample will fail. So at that time, whatever be the A, F, it will correspond to the final failure case, correct? And the value of it varies from minus 0.5 to 1.5, fine? Now, after that, we have studied, now we are aware with the pore-water pressure equation, the change in the pore-water pressure equation, then for triaxial conditions, how it's getting modified. Now, during the different stages of a triaxial test in the next section, I think sir will go through the triaxial testings. So briefly, in the triaxial test, we have a confining stage. Initially, it is a saturation stage. after saturation it is confining stage, and after confining stage we have the loading or shearing stage. Now in the last two stages, confining stage and the loading stage, how this delta U can be written for these two stages, correct? So in the confining stage, when we are confining the stage in this sample, the radial stresses are equal, whatever be the horizontal stresses that are equal to the vertical stresses. So this sigma delta sigma R is equal to delta sigma 1 is equal to delta sigma 3, correct, for the confining stage. Now what is the delta U? Delta U is B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3, correct? Now for the confining stage, since its R round stress are equal, this can we use this here? Delta sigma 1 is equal to delta sigma 3. So this term, this whole term will become 0. So we will remain with B times delta sigma 3, correct? So here, that's why I have written it in terms of B into delta sigma 3 plus A times delta sigma 3 minus delta sigma 3, because delta sigma 1 is equal to delta sigma 3 in the confining stage. So the equation will reduce to delta UC, which is the change in the pore water pressure during the confining stage. It will be equivalent to B times delta sigma 3. So this B is equivalent to delta U by delta sigma 3 is for the confining stage. And this is one of the criteria that we use in order to check that whether the sample is saturated or not. And for the saturated sample, this B is approximately 1, but in the experiments we never reach B squared 1. So in the experiments we will say if B is greater than 0.95, we will say the sample is saturated in the saturation stage. And again we can do a check in the confining stage whether the sample is saturated or not. Now for the loading stage. Now the loading stage, so loading stage is or we are sharing the sample once the sample is fully consolidated, and at that time this B value is 1, fine. So B is 1 during the loading stage, and what we are doing, what causes the failure of the sample is the additional derivative stress delta sigma D, correct? So delta U D, this is the change in the pore water pressure due to the derivative loading. So it will be equivalent to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. Now in the sharing phase, what we are doing, we are actually applying the load from the top or stresses from the top, sigma D, but we are not changing the sigma 3. Sigma 3 is what it is after the consolidation, let's say 100 kPa. So there is no change in the confining stress. So the change in the confining stress is 0. So delta sigma 3 will be equivalent to 0. So as a result, this equation will be simplified to AF is equal to delta UD divided by delta sigma 1. So at the failure, once the sample fail, so A at failure will be equal to, I told you there will be two A's. One is corresponding to initial loading and corresponding to final loading. So AF is equal to delta UD at failure and delta sigma 1 at failure. Therefore, the total pore water pressure equation will be equal to delta U. You can write here C confining stage and delta U at the during the derivative or the derivative loading. The pore water pressure that will develop in the sample during the confining stage and during the derivative stage. Now, this is one way of representing the pore water pressure equation. Now, there are other ways of representing this increase in the pore water pressure equation. This was the initial how the Skempton developed it. Now, with further adjustments, we can write as delta sigma is equal to B times 1 by 3 delta sigma 1 plus 2 times delta sigma 3 plus 3A minus 1 by 3 delta sigma 1 minus delta sigma 3, correct? Now, if you remember for the triaxial condition, this term, I will bring it here, 1 by 3 sigma 1 plus 2 times, not change, in general I will write sigma 3, it represents the mean stress, correct? And sigma 1 minus sigma 3 represents the deviatoric stress. It represents the deviatoric stress. So it means that this delta U is a function, or it depends upon the both mean stress as well as deviatoric stress. And this is for the purely like in general equation I am telling. But if we talk about the elastic material, if soil behaves elastically, this A will be equivalent to 1 by 3, as I told you in the previous slide. So this A will be equivalent to 1 by 3, this term will reduce to 0. So it means that delta U, the change in the pore water pressure, it only depends upon the mean stress for the elastic soils and not on the deviatoric stress. However, If A is not equal to 1 by 3, then the derivative stress has a significant influence on the delta U, as you can see here. Correct? Fine. Now, why this overall parameter B dash? This B dash is actually taken into account the change in pore water pressure due to the change in the loading or change in the total stresses. Delta sigma 1, I can see. Now, delta U is actually taken care of. This B dash is actually taking care of the change in the pore water pressure that will happen due to the delta sigma 1. And the formulation for that are delta U divided by delta sigma 1 is equal to B times 1 minus 1 minus A into 1 minus delta sigma 3 by delta sigma 1. Now this was the all about the pore water pressure equations, Skempton's pore water pressure parameters A and B, then different formulations for understanding the different for understanding the influence of mean stress, derivative stress, elastic properties on the pore water pressure. Now earlier we saw for the triaxial condition we developed the equation, correct? We developed the equation for the triaxial condition, not this here, this one. Now for the plane strain, which is more prevalent, or we can say in the field, in most of the geotechnical problems are considered as the plane strain kind of problem as compared to the triaxial problems. And we know from the previous lecture that for the plane strain case, for a plane strain problem, this strain in the longer direction is considered as 0. Why? Because we are assuming that one dimension is very large as compared to another dimension, so the strains in that direction are considered 0. And if we relate that strain to the corresponding stress using the constant relationship, then this is given by sigma 2 dash divided by E minus mu divided by E sigma 1 dash plus sigma 3 dash. Here with this equation we will be able to determine the sigma 2, that is the intermediate stress. So delta sigma 2 is equal to mu times delta sigma 1 plus delta sigma 3. Now again we will put this equation C in the initial formulation of the delta U. Can you see here? We have to put it here, correct? So once we will replace this delta sigma 2 here, we will get the pore water pressure equation for the plane strain condition. And the only one difference you will observe is that this parameter A in the triaxial was 1 by 3, but in plane strain it's 1 by 2. So 1 by 2 for plane strain and 1 by 3 for the triaxial condition. Fine. Now as I told you that there were a lot of attempts for determining the excess pore water pressure during the different loading conditions. One such attempt was done by the Skempton, and another one such equation or attempt was done or given by the Henkel. So Henkel's pore water pressure equation in terms of octahedral stresses, he gave in terms of octahedral stresses. So as per his equation, delta U, that change pore water pressure, is equal to beta times the delta sigma octahedral plus 3 times alpha into octahedral shear stress, octahedral normal and octahedral shear stress. And tau sigma octahedral is equal to P and tau octahedral is equal to root 2 by 3 for the triaxial condition. So accordingly the equations will be modified as delta U is equal to beta times delta P plus 3 times alpha root 2 by 3 delta Q. And this alpha beta are the pore water pressure parameters, and beta is equal to 1 for fully saturated soils. So Henkel has A and B. This Skempton was having A and B as a pore water pressure parameter, and now this Henkel has alpha and beta. Now, how we can relate these two pore water pressure parameters alpha and A for a condition if we have a constant sigma 3? Please remember, constant say radial stress during compression of saturated clay. These two terms are important. I will just like to highlight them. One is the constant sigma 3 and saturated clay. Why these are important? Because these two conditions will tell us we can use these conditions in the equation formulations for the Skempton's equation and the Henkel's equation, and as a result of which we will get a relation between them. So for a constant sigma 3, it means that delta sigma 2 is equal to delta sigma 3 is equal to 0, and beta is, we can't write beta is equal to 1, we can write simply beta is equivalent to 1. So we can write as beta is equivalent to 1 and B is equivalent to, correct? So as per the Skempton's equation, delta U is equal to beta times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. So if you use this assumption, we have a constant sigma 3, so this will reduce to 0, this term will go to 0, so delta U is equal to A times delta sigma 1, correct? Now for the Hankel's equation, so delta U is equal to beta times delta P plus 3 times alpha root 2 by 3 delta Q, correct? So delta P is the mean stress, delta sigma 1 plus 2 times delta sigma 3 by 2, this will reduce to 0, so it will be equal to delta sigma 1 by 3, and delta Q is delta sigma 1 minus delta sigma 3, since this is equal to 0, it will be equal to delta sigma 1. So delta U will be equivalent to delta sigma 1 by 3 plus 3 times alpha root 2 by 3 delta sigma 1. So after doing the change or readjustment, we will get alpha is equivalent to 3 times A minus 1 divided by 3 times root 2. This is the equation or relation between the Hankel's pore-water pressure parameter alpha and Skempton's pore-water pressure parameter A for the case when we have constant sigma 3 and the soil is fully saturated. After that, there is one more important topic to discuss. After that, we will come to the numericals. It's about the effect of sampling of soil in the field on the pore-water pressure. Like you would have observed that when we are going to the field for taking the sample, for the clays generally, when we take the sample out as an undisturbed sample, they can withstand their shape, or they are not collapsing when we take them out like the cohesionless soils. Or if we have a pure cohesionless soil, they may crumble as we take them out. They can't stand. But if we take the sample of the cohesive soils from any depth as an undisturbed soil sample, then they are able to withstand. They are not collapsing at all. So what causes this a sample of clay or the sample of the soil to withstand of its own without being crumpled or without being damaged? So this that's why we are like it's all a play of pore water pressure that is happening during the extraction of the soil sample. So that's why the effect of sampling on the soil becomes important, and this all is a play of the pore water pressure. Let's assume that we have to take a soil of sample from the field which is at a depth of let's assume I would say it's a depth of Z minus H. I think this Z will be up to here only. Sorry, this is correct. Yeah. So we have to take the sample from A point, and there's a water table at a depth of H. So ground level is here, and the unit weight of the soil here we are assuming it to be bulk unit weight, and we have a saturated unit weight for the soil, and we have the stresses acting on the soil sample A, sigma V and sigma H. Now the soil is saturated and the conditions are equilibrium. We have the equilibrium conditions. So sigma 1 will be equivalent to sigma vertical, and sigma 2 is equal to sigma 3 is equal to sigma H. So what are the vertical stresses acting at point A will be equal to the overburden stresses. That will be equal to gamma H plus gamma set into Z minus H. Correct? Now similarly, what is the pore water pressure? Initial pore water pressure will be equivalent to the Z minus 1 Z minus H into gamma W, initial pore water pressure at this site. Fine. Now, what are the vertical stresses acting? What are the vertical effective stresses, which will be equal to gamma into H plus gamma saturated into Z minus H. Fine. Now, the coefficient of earth pressure at rest, K0 is equal to sigma vertical divided by sigma horizontal. So with this equation, we'll be able to determine the sigma H. Correct? So sigma H is equal to sigma H dash plus Ui. So we'll be able to determine the sigma H dash. From sigma H dash, we will get the total stress parameter sigma H. So sigma H is equal to sigma H dash plus Ui. Ui is the initial pore water pressure. Correct? Now this sigma H is equal to K0 times sigma vertical plus Ui. Now we got the stress state. Like we determine the sigma V and the sigma H for the soil. Now when soil sample is sampled from the subsurface, the confining stresses are released. So sigma 3 is 0. So this change in the stress condition induces the change in the pore water pressure. Fine. So this change in the stress condition induces the change in the pore water pressure. So this all exercise we did for determining the sigma V and sigma H. Now, when the soil sample is sampled, the confining stresses are zero because there is no stress acting at the point when we take it from the soil. So therefore, can we use the Skempton's equation? So delta U is equal to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. Since we are assuming it is a saturated sample, B is equal to 1. So therefore, this fine. So B is equal to 1. So delta sigma 3 is the change in the confining stress. So there will be final confining stress minus initial confining stress. Since after sampling it out, this confining stress is to 0. So therefore, the delta sigma 3 is equal to minus sigma H, and delta sigma 1 is equal to sigma 1 final minus sigma 1 initial. Final sigma 1 is also 0 because there is no confinement for the sample. There is no sigma 1 ample for sigma 1 applying on the soil sample, and sigma 1 initial is the minus vertical stresses. So delta U can be written as minus sigma H plus A times minus sigma H plus sigma vertical plus sigma horizontal. So which will give us the final formulation. UF is equal to here we will get delta U is equal to minus A times sigma vertical minus 1 minus A into sigma horizontal. So change in U will be equivalent to U final minus U initial. U final is equivalent to delta U plus UI. Delta U is this and UI is the initial pore water pressure that we have determined here, this one. So this is the final equation for the pore water pressure for the sample of the soil that has been sampled out. Now for the NC soils, A is positive and close to 0.5. For the normally consolidated soils, this A value is 0.5 and it's close to 0.5. So it means that this term will be less than this term. So UI will be greater than UF. It means that final pore water pressure is less than the initial, which will impart a suction kind of thing in the sample. So it results in the effective stresses. This suction will cause the increase in the effective stresses, which will hold the soil structure together without collapsing. So this is the reason why when we are taking the undisturbed samples out from the subsurface or from the greater depths, so they are holding the structure because of the reason that there is an additional negative pore water pressure or suction, which actually results in the effective stresses which hold the soil structure together without collapsing. So this is all that we have studied in this the content of week 5. So now we will go through some problems. In case you have any doubt, I will wait for 5 minutes. After that, we can start the numericals. Okay, so we will start the example problems. These are based on the Skempton's pore water pressure equation, then the Henkel and all. So the first problem. So we'll start. So in a CU test on a normally consolidated clay, so consolidated undrained test on the NC clay, a sample consolidated under a stress of 200 kN per meter square failed at a deviatory stress of 150 kPa. The pore water pressure at failure was 75 kPa. Calculate the final pore water pressure parameter A of Skempton pore water pressure here. So what is given? So solution. So in a CU test on NC clay, sample consolidated under stress of 200 kPa. So sigma 3 is given. Sigma 3 is given as 200 kPa or kN per meter square. It failed at a deviatic stress of 150. So this can be considered as failure, and it failed at a deviatic stress of 150. So sigma D failure is equivalent to 150 kPa. Correct? Fine. Is it okay? what is the U at failure, pore water pressure at failure is 75 kilonewton per meter square. These three things are given to us. So this is the since the deviated stress is being applied on the sample and the sample is consolidated, correct? Sample is consolidated. We will write since sample is consolidated, what will be the B value? B value will be 1, correct? And also the like the stage of loading is the loading stage. The loading stage B value is generally taken as 1. So can you write the equation? Delta U is equivalent to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3, correct? Now in the during loading stage, or we can say shearing stage, sigma 3 is constant, correct? We have studied that. Therefore the change in delta sigma 3 will be 0. It means that this term will go to 0, this term will go to 0. So what we are left with? We are left with delta U is equal to A times delta sigma 1. So at the failure we can write it as delta U at failure is equal to A times delta sigma 1 at failure. So which means that AF is equal to delta U at failure divided by delta sigma 1 at failure. What is the change in U, or the pore water pressure at final, or we can simply write as U at failure divided by sigma 1 at failure. It's 75 divided by what is the deviated stress at failure? It's 150. So AF will be equal to 0.5. So the parameter A at failure comes out to be 0.5, correct? So how we approach this problem? We first write down what are the things that have been given. So since the sample is consolidated, which means that B is equal to 1, so the equation further becomes easy, because this B is equal to 1, we have not only one parameter. And again, during the loading stage or the shearing stage, this confining stress is constant, sigma 3 is constant, so which means that the change in the sigma 3 is 0, which means that this term and this term will go to 0. So we are left with delta U is equal to A times delta sigma 1, right? Now let's move to the next question. So next question is, in a triaxial test, a soil sample was consolidated under a cell pressure of 700 kPa and bag pressure of 350 kPa, correct? So the sample was consolidated at 700 and 300 kPa. Thereafter, with drainage not allowed, the cell pressure was raised to 800 kN per meter square, which resulted in the increase in pore water pressure reading to 445. And the action load was then increased to give a deviated stress of 575 kN per meter square. Sigma 3 is constant at 800, and a pore water pressure reading of 640 was observed. Find the pore water pressure coefficients B and D. It means that the soil sample was consolidated at 700 and 300 kPa, and drainage was not allowed, and after that the cell pressure was increased to 800 kN per meter square, and as a result of this increase, the increase in the pore water pressure reading was 445, and the actual load was then increased. After this case, it was then increased to a deviated stress of 575 while the sample has failed, and at this 575 the sigma 3 was held constant at 800 fine, and the pore water pressure reading was 640. So we try to solve it. So we will write it here. During consolidation phase, what is the cell pressure and what is the bag pressure? 350 kPa, correct? Now it has to be noted very clearly, and in the next session I guess it will be teached to you that during the consolidation phase, when we are increasing the bag pressure, like we have two increments in the consolidation phase. At the end of the consolidation phase, once the consolidation phase is over, the pore water pressure is dissipated. So the pore water pressure transducer will take the reading, or it will show the reading, which will be the reading corresponding to the bag pressure. So whatever be the bag pressure at the end of the consolidation stage, that will be equivalent to the pore water pressure, correct? So I will write it here. Once consolidation is over, excess pore water pressure will be dissipated, and whatever will be the bag pressure, the pore water pressure will be equal to that value of bag pressure, correct? So it means that initial U initial is equivalent to bag pressure, it is equivalent to 350 kPa, fine. And after that the cell pressure was increased to 800 kN per meter square. So what is the change in the sigma 3? The change in sigma 3 is 100, and this increase from 700 to 800 caused the pore water pressure reading to increase to 445. So U final is equivalent to U final is 445. I mean for this stage up to this point is 445 kPa, fine. Now can you find the B parameter? So for the saturation phase, so delta U C is equivalent to, or simply delta U, not write C, is equal to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3, correct? Fine. So during the confining stage, the delta sigma 1 is equal to delta sigma 3, so this will reduce to 0. So we will get delta U by delta sigma 3 is equal to B. So this B is equal to delta U is 445 minus initial is 350 divided by change in the confining is 100. So you will get 0.95. Now for the at shearing stage, so what are the values? B is 0.95 and the change in the confining stress is equal to 0. So what's Skempton's equation be equal to? Delta U is equal to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. This term will be 0, this term will be 0, so we are left with delta U is equivalent to AB into delta sigma 1. Now either we can find AB, like we know that A dash is equal to AB, or we can use the value of B. So delta U is equal to 0.95 times A into delta sigma 1. So this delta sigma 1 is a change in the dielectric stress. Like delta sigma 1 is equal to delta sigma 3 plus delta sigma d. So this delta sigma 1 be equivalent to, it is telling that the axial load was increased to give a dielectric stress of 575. So the change in delta sigma 1 be equivalent to the dielectric load. So and delta U will be equivalent to the final pore water pressure rating, that is 640, and what was the final reading in the confining, that is 445. So it is A is equivalent to delta U is 640 minus 445 divided by 0.95 times 575. It comes out to be 0.357. Fine. So the A parameter and B parameter we have determined. So A is equivalent to 0.357, B is equal to 0.9. Fine. So what we did initially, the concept was that during the once the consolidation is over, the excess pore water pressure will be dissipated, and whatever be the back pressure, the pore water pressure equal to that value of back pressure. It means that at this stage, this initial pore water pressure was 350, and when we change the confining stress to 700 to 800, there is an increase in the pore water pressure to 445. It increased to 445. So the change in pore water pressure was 445 minus this, and the change in confining stress was 100. So we will get the B value. Then the question is telling that the axial load was then increased to get dielectric stress of 575, and a pore water pressure reading of 645 was observed at a constant sigma 3 of 800 kP. Find the pore water pressure constant. Now at this stage, the shearing stage, B is 0.95 and delta sigma 3 is 0. We use these two conditions. And we came up with this equation: delta U is equal to 0.95 times A into delta sigma 1, and delta U is a change in pore water pressure in the shearing stage minus in the confining stage. So it was 640 in the shearing and 445 in the consolidation stage, and delta sigma 1 is a change in the vertical stress, that's equivalent to 575. So with this we get A is equal to 0.357 and B is equal to 0.95. Correct? Now we have another question. A uniform vertical load of 145 kN per meter square is applied instantaneously over a very long strip. Please note down, it's a very long strip. And it's applied instantaneously. It means that there will be the generation of pore water pressure. Estimate the delta U that will be developed due to loading at point A. Assume that U, Cohesionless ratio is 0.45 and A is pore water pressure parameter. A is 0.6, and this is the pore water pressure corresponding to the Skempton equation. And the stress state of the soil at A is given as sigma z is equal to 118.6 kPa and sigma x is equal to 26.39 kPa. Now, first thing that should come to your mind is it's a very long strip of vertical load. It means that the conditions will be a plane strain condition. So conditions will be a plane strain condition. So I will write plane strain condition. Plane strain conditions will be here. Fine. It's given that sigma 1 is equal to sigma z is equal to 118.6 kPa, and sigma 3 is equal to sigma x is equal to 26.39 kPa. Now for a plane strain condition, we know that the intermediate stress sigma 2 is equal to mu times sigma 1 plus sigma 3. Correct? We have written it here, right? For a plane strain condition, where it is, yeah, here. have written it here. So what will be the sigma 2? Sigma 2 is equal to mu times mu 0.45, and we will write 118.6 plus 26.39. So sigma 2 is equal to 65.25 kilonewton per meter square. From here you can either use that like the general equation of Skempton's equation, or you can use the Henkel's. I will go with the Henkel because the reason for that is because you will get to know the relationship between the alpha and A, how we are using that. So we know that delta U is equivalent to beta times delta sigma octahedron, but since this beta is equal to 1 for the saturated size, so better to write without that 3 alpha times delta octahedral shear stress, correct, since beta is equivalent to 1. Fine. Now for this case, when we have a sigma 1, sigma 2 and sigma 3, sigma 1, sigma 2 and sigma 3, how we can determine the tau octahedral and sigma octahedral? We know that sigma octahedral is given by the average of these three, sigma 1 plus sigma 2 plus sigma 3 divided by 3, which can be written as 118.6 plus 26.39 plus 65.25 divided by 3. It will come out to be 70.08 kPa, and this tau octahedral is equivalent to root 2 by 3 of Q, which is equal to root 2 by 3 into Q is sigma 1 minus sigma 3. So root 2 divided by 3, sigma 1 is 108.6 minus sigma 3 is 26.39. So this tau octahedral will be equivalent to 43.468 kPa. And now we have got this, we have got tau octahedral, sigma octahedral and tau octahedral. What about this alpha? We know the equation that we have developed for the alpha relating with A. This alpha is equivalent to 3a minus 1 divided by 3 root 2, which is equivalent to 3 into 0.6 minus 1 divided by 3 root 2, which is equal to 0.189, correct. So we got all the variables in this. So can we determine delta U? So delta U is equivalent to delta sigma octahedral, that is 70.08 plus 3 into alpha is 0.189 into tau octahedral, that is 43.468. So delta U comes out to be 94.72 kPa. Fine. So you can use the another equation for determining the pore water pressure. Why I use the Henkel? Because I want to show this relationship also, how we use this and how we are using the sigma and tau octahedral for determining the pore water pressure, increasing the pore water pressure, correct. Fine. Now coming up to the last question. After that we will have a discussion session. So the question is, we have a undisturbed normally consolidated clay with B is equal to 1 and A is equal to 0.6. It's taken from a depth of 12 meter below ground space, wall table at 3 meter from the ground level. Okay, we'll draw it first. So this is the, let's assume, ground level, and we have taken a sample from, let's assume this is the sample. Okay, let's call it A, and the depth of this point is 12 meter. And now there is a water at a depth 3 meters from the ground surface. Here we have water, and the depth is 3 meter. Okay, now for this condition we have been asked, assume homogeneous deposit and undrained sampling, determine the final pore water pressure in the sample immediately after extraction. What is the final pore water pressure once immediately once we are extracting the sample, right? So the parameters given are gamma bulk of this soil is given, gamma bulk is given, gamma saturated is given, and water at rest condition the if this what we call is K is given. Earth pressure coefficient at rest condition is 0.55 it's given. So first of all, what we will start with, we will first start we have to first determine the vertical and horizontal stresses, correct? So what are the vertical stress or in terms of total stresses? So 17 into 3 plus 19 into 9, correct? Total stress, this is 9, sorry, this is 3 meter, this will be 9 meter from here, correct? So this total vertical stress is equivalent to 222 kPa. Fine. What is the initial pore water pressure, or the equivalent pore water pressure will be the the depth from which the water table is there, or from A, the depth will correspond to the point at which the water table is present to the depth where we have considering the soil element. That is 9 into 10, that is 90 kPa. Fine. Now sigma V dash is equivalent to sigma 1 dash, which is equivalent to 222 in terms of effective stress parameters, 222 minus 90, which is 132 kPa, correct? Why? Because this K, this earth pressure coefficients are written in terms of effective parameters, correct? So corresponding to the sigma 1 effective vertical stress, what is the effective horizontal stress? Sigma 3 dash is equal to K naught times sigma 1 dash, which will be equivalent to 0.55 into 130 to 72.6 kPa, correct? Now corresponding to this effective horizontal stress, what will be the total horizontal stress? Sigma H, it is 72.6 plus pore water pressure is 90, it is 162.6 kPa. Fine. Now comes the important thing. So when we are extracting the sample, during extraction, or when the sample is extracted, when sample is, or we can write when soil is sampled, when soil is sampled, so it means that the confinement will be reduced to 0. So when the confinement is reduced to 0, since it is a saturated sample, so B value is 1, so sigma 3 will be 0, and the corresponding change we have to determine. Now we'll again write the equation, delta U is equal to B times delta sigma 3 plus A times delta sigma 1 minus delta sigma 3. Now what is the value of delta sigma 1? Change in the vertical effective stress will be equal to sigma 1 final minus sigma 1 initial. Since there is no confinement in the sample now, so the sigma 1 F is equal to 0, and this sigma 1 initial is equal to sigma V, correct? And delta sigma 3 is equal to sigma 3 final minus sigma 3 initial. 0 due to confined, there is no confined, sigma 3 final is 0, and sigma 3 initial is equal to sigma horizontal. So delta u is equal to b is 1, so delta sigma 3 is minus times sigma horizontal plus a times minus sigma vertical plus sigma horizontal. Minus into minus is plus. So delta u comes out to be minus sigma horizontal minus a times sigma vertical plus a times sigma h, or it can be written as, if we take sigma h is common, so it will be equivalent to minus a sigma vertical minus 1 minus a sigma horizontal. So minus sigma horizontal follows this. Fine. So this is the change in the pore water pressure. Fine. This is the change in pore water pressure due to sampling. Fine. Now we know that final pore water pressure is equivalent to initial pore water pressure plus the change. Now what was the initial static or equilibrium pore water pressure? I think it was 90. It's 90 plus delta u is equivalent to minus a sigma v minus 1 minus a sigma h. It's 90 plus minus, what is a? A is 0.6 into sigma vertical is 222 minus 1 minus 0.6 into sigma horizontal is 162.6. So it will come out to be minus 108 kPa. So u final is equivalent to minus 108 kPa, which means that there is a suction in the sample, which is actually holding the sample at its position. So this, as I told you in the last this conceptual slide, that it results in the effective stress which holds the soil structure together without collapsing. So this suction is actually creating the pseudo effective stresses, which is actually holding the soil sample at its place. Fine. So that's all numerical problems that I want to solve with you. I hope these 4 problems and the discussion over the content will be helpful for you to you will be able to solve the assignment problems, because all the assignment problems, they have the same concept which I have used in this example problems and all. So I will wait for few minutes for the discussion. After that, and the session will go like this. If you have any doubts, I will be here after 5. I will mute this. If you have any doubt, you can just raise your hand or ask here, or you can ask the questions in the doubt form, while the mentors will be there to give the solutions or answers to you as soon as possible. Fine. So I will stop the recording here, but I will be here in the meeting after 5. So if you have any doubts, you can ask after that. So hope that you will solve all the problems in the assignments. Thank you. I will just stop the recording, but I will be here in the session up to 5.